So thanks Arnab and Pinaki for letting me speak in this conference. So I am Marup, I am a PhD student at this institute, and today I shall introduce you to a new kind of or model of resetting known as the fast passage resetting. I guess there was some talk, some discussion in Shotto's talk with Bulbul and Shotto, so that when the system crosses a certain threshold, you reset rather than drawing it from some random from some distribution. So this was done with Arnab and Shotto in collaboration, and so I guess you have already heard about what is resetting and all these things are all about. So let me just give you a brief intro. So the idea of stochastic resetting started with this seminal paper by Martin and Shotto, where they first studied the stochastic resetting in a simple 1D diffusion. So in general, suppose you have a system which starts at time t is equal to 0 and it finishes at some time t. By resetting, you mean you do not allow the system to evolve continuously. In midway, you stop the system and bring it back to the initial configuration again. If you see this animation, you can see that there is a particle which is moving randomly, but at some random time shown by these arrows, you hold the particle and bring it back to the starting position again. So this is what we mean by resetting, like starting from scratch. And it's not moving. Oh, I see. So I guess resetting has mostly two cornerstones like this non-equilibrium properties and its fast passage properties, and that is why it is found to be useful in several contexts, starting from several systems from physics, chemistry, and even extending up to economics and computer science. However, more recently, around 2020, Redner and collaborator introduced the new idea of fast passage resetting. So what it means is, rather than resetting at some random times drawn from some distribution, you reset when the system crosses some threshold. So in this figure, there is a 1D motion and there is a target at x is equal to L. Whenever the particle crosses this x is equal to L target, the system immediately resets. So in this case, the resetting is governed only from the system itself. There is no external times or distribution involved. And if you want to draw a comparison between this traditional resetting setup with the Shotto and Evans model, here the resetting times are externally decided, not independent of the system. But in the fast passage resetting, the resetting times are dependent solely on the system itself. It does not come from some external distribution. And in this paper, Redner and all, they have mostly studied all the probability distribution and cost function associated with this fast passage resetting mechanism. However, the target search problem with this fast passage resetting mechanism is still unexplored, and this is what we intend to do in this. Yeah. So let me just tell you what the system is. So there is one resetting target here, and there is another target which is the global target, which is your ultimate target. So the job of the resetting target is to reset. Whenever the system crosses this resetting target, you immediately bring the particle back to the original position again. And this global target is your ultimate target. Whenever the system reaches this global target or the only target in your system, you note the corresponding fast passage time. So in summary, there are two targets. One is the threshold of the resetting target, where the job of that is to reset, and there is the global target, which like when the particle reaches this global target, you note the corresponding fast passage time, and you want to analyze that time itself. So this is the 1D Brownian motion, and you can see when the particle reaches here, it just comes back to x0 again until it finds the global target. So this is the plot of the MFPT, which is a monotonically decaying function. So let's just spend some time to understand what is going on here physically. So this parameter u is just the ratio of x naught by L, and just take the first the extreme limits when u goes to 0. When u goes to 0, you can also consider this as L going to infinity limits. That is, your resetting target is at infinity. When your resetting target is at infinity, so that there is no resetting target in your system, and this is just a 1D Brownian motion with only one target, and the mean fast passage time is infinity. And because there are physically there are trajectories which will go far away from the global target, and it will take infinite amount of time to come back. So your mean fast passage time goes to infinity. So it is actually infinity because of certain cutoff. I have to there's finite. It is actually infinity in this limit. However, when you put a certain resetting target at a constant, some certain value of L, there two things happen. One, it does not allow the particle to go in a much diverging direction. Like it does not allow the particle to go much distance away from the global target. And the second thing is that it helps the particle to come towards the global target. Whenever the particle reaches the resetting target, the target says, no, you have come in the wrong direction, just go towards the global target. So the presence of the resetting target helps in the search process. That's why when you have a particular some finite value of u, the mean fast passage time is a finite quantity. And the more closer the resetting target is to the starting position, the better you do, because the better you are cutting off those diverging trajectories. So even without doing any calculation or anything, just by simple intuition, you can say what is going on there. Like you can simply infer this curve. So to see some more interesting behavior, let us go to the collective search process. Yeah.
Does the input passage time depend on the value of L, how far the reset?
Yeah, absolutely. So they actually they depend on the value of L and also the x naught. And you can show that you can scale the MFPT with respect to x naught, so that it only depends on the ratio of x naught by L. By collective search process, I mean there are n searcher, independent searcher who searches in parallel. So in the figure, I have shown three particles. You can assume there are n number of particles who start simultaneously from x naught, and whenever any of the particles reaches the global target for the first time, you stop the process and note the corresponding search time or the fast passage time. And in the context of extreme value statistics, this is known as the fastest fast passage time. And for the paradigmatic Brownian motion, the result is already well known, and it is seen that when your number of searchers are greater than or is equal to 3, the mean fastest fast passage time is finite. For n is equal to yeah, I just wanted to give in. sorry. Yeah.
What is the boundary condition?
Yeah, boundary. So there are two boundaries. One is, so in this process there is only one boundary, is the global target. Whenever any of the particle reaches this boundary, you just note the corresponding fast passage time. Absorbing boundary. Yeah, it's like absorbing. Yeah. So here in this process there is only one target is there. I will come to that. So the question is, can this fast passage resetting mechanism, like as I was asking, if we put another boundary there, can it do better than this underlying reset free process? So this problem with the traditional resetting setup, where you reset depending on some external distribution, was already studied in some series of papers by Shrotto. Mostly this one, where the notable result was that there exists a critical number of walkers below which traditional resetting will help to expedite your search process compared to the reset free process. So, but as I started with, I want to study the effect of fast passage resetting on this system. So our work consists of the same n searchers in parallel, however with a resetting target here. So again there are two targets, resetting and global target. Again the particle starts from x naught, but now if any one of the particles reaches the resetting target for the first time, you reset all of the particles back to the starting position again. And again they restart their search process. And they continue doing so until one of the searchers finds the global target. So this is the collective search process with first passage resetting, where resetting occurs when any one of the particles reaches the resetting target. Now let us see how the MFPT looks like in this setup. So when you plot the MFPT, again you can scale it with respect to u, like x naught by L. There are several things to notice here. Let me just illustrate the limiting cases first. Take the limit u going to 0. It is the same as when your L is infinite. That is, there is no resetting target in the system, and you get the simple reset free processes result. And this is shown by these dashed horizontal lines. And when you go to the limit u going to 1, that means the particles are starting very close to the resetting target, and the resetting is very frequent there. Note that these solid lines, which is the MFPT of the with FPR, goes beyond these dashed horizontal lines for some range of u. That means in this region, MFPT of with first passage resetting is already lower than your reset free process. So MFPT, so the first passage resetting can indeed enhance your search process compared to the reset free process. There is one more aspect of it, that is the optimality with respect to u. So if you plot any, suppose notice the inset. So here I have just zoomed out the plot with n is equal to 3, and you can see there is the existence of a optimal value of u. Like if you just remember this resetting with rate, you can draw analogy with the optimal resetting rate here. So yeah, so there is u optimal, and you can show the variation of the u optimal with respect to n. It goes like this. More interesting feature shows up when you plot the MFPT with respect to the number of searchers. So these solid lines denotes the MFPT with FPR, and you can see these curves are again non-monotonic in nature. So take the plot with u is equal to 0.6, and you can see there exists a n optimal for which the MFPT is the lowest one. And you can again plot this n optimal with respect to u, and you can see there is certain critical value of uc beyond which n optimal is simply 1. That is, the plots are monotonic in these regions. However, if your u is less than uc, your the curves, the MFPT will be non-monotonic with respect to number of searchers. More interestingly, note this dashed line. These dashed lines correspond to the reset free process. That is, there is no resetting target. So whenever these solid lines lies below these dashed lines, your MFPT with FPR does better than the reset free process. They crosses around some region like NC, and whenever your mean number of the number of searches is lower than this NC, your MFPT with FPR is better than the reset free process. Yeah, so that's all I have to say. The central idea is for n greater than 2, you see interesting optimization behavior with both with respect to number of searchers and also the ratio x naught by L. And again, there exists a critical number of searchers beyond which you can expedite your reset, search process with fast passage resetting. Thanks.
Oh, okay, so like, I mean, like, if you do the same thing, I mean, just a model, okay? I mean, if you do the same thing with one side reflecting boundary,
Yeah.
and you do the usual traditional resetting.
Right.
I mean, what would, won't it be more efficient than this?
That needs to be checked. I guess. Yeah. Because
I mean, like, in the other case, like, you are getting the, I mean, like, reflection boundary, but then, I mean, in a sense, reflecting, you are actually resetting at the first passage point also. Not in the sense, it bounces back in the usual diffusive process, but it.
even like, even you can check, like, even if you just forget the reflecting boundary, it will be interesting to check even if it does, the fast passage resetting does better than the traditional resetting. You can compare those two itself. You can put a, but it is something to check, I guess.
Yes.
It's just okay.
So I have a question on the last two plots that you showed on the mean first passage time. I did not understand what difference between those two plots were like and the previous slide.
This one?
Yes.
Yeah, this one is with respect to x naught by L. X naught your starting position and L is the resetting target's position.
Yeah.
And this one is with respect to the number of searchers.
Okay. Yeah.
Yeah.
Right, okay. Thank you.
Just want to understand. So your first passage is when the first seeker reaches the global target.
Right. Yeah.
You
Out
don't
of the-
worry about the total ensemble, how much time it takes
No.
to reach this.
No. If any one of them reaches for the first time, we note the first passage time. This is the fastest first passage time out of n.
And how is it interesting in terms of real life situations? Because if you have many seekers, wouldn't you want to seek globally when they reach the target? I mean, I'm just asking, I'm just curious about that.
Yeah, if you, in real life situation, this fast passage resetting, I guess, was already discussed, like, I guess, in some discussion around, there are some physical scenarios where you can see, like, for example, neuron firing or, for example, shattering of a cluster when it reaches a certain threshold value. But how the n particle fast passage resetting can be modeled to a real life systems, I guess that needs to be thought.